So last week we talked about last week, 2 weeks ago, right?
Mhm.
I'll just keep saying last week because it makes more sense to me. So we talked about Big Bang Theory, right? Blake, you ready with your notes from last week? Okay. What did we talk about? What was the big thing that we killed everyone's bubble?
It wasn't an explosion.
It wasn't an explosion, right? That's really sad.
Frowny face.
Right, Julie?
Yeah, I made a frowny
I
face.
watched it this morning.
I've been angry
Thanks,
about
man.
it.
I think that
I had to get my daily fill of Tim.
Yeah,
So-
I think that bumped it up to 4 views. I'm not really sure. I think I looked yesterday and it was 3. So
I watched it this morning.
do you watch? You should watch it twice.
I may.
5.
I'll watch it tomorrow.
Okay.
So then.
Sweet. So we talked about Big Bang Theory, and it's not an explosion. It's just this quick expansion, right? And all these different processes that are supposedly happening, and then we formed stars. And today we're going to talk about planets, right? So today we're going to talk about Earth and the age of the Earth. So we didn't get to last week the perfect planet section of your notes, so I added it to this week's notes just for you guys, because that's how I roll. Okay, so we're going to talk about a couple of characteristics of Earth that give it really the ability to sustain life, right? So one of the big things now is searching for a new planet that can sustain life, right? So it has to have certain characteristics so that we as humans could exist on that planet. Probably not going to happen, right? Because it's not in the Bible. You know, we're here on the earth, and then God judges us here on the earth, right? So, bummer. But it's probably not going to happen. But we can see God's design and God's amazing creation in the different characteristics of the planet. So the first one we're going to talk about is the location. So this is going to be a terrible drawing, okay, Brandon? There are good ones coming, but this one's going to be terrible, okay? So we're going to look at our galaxy, right? What's our galaxy called?
Milky Way.
All
The Milky
Milky Way.
Way. How about that? You guys know stuff.
It's delicious.
What kind of galaxy is it?
A big one.
Space one.
Spiral galaxy,
Uh-huh.
right? So the galaxy is turning, and it has these characteristic arms that are coming out, which are stars, right?
Oh.
So for Earth is located in an arm that doesn't have a bunch of stars. So if you look at the spiral galaxy, you'll see these gaps where there aren't as many stars. And this is where Earth is situated, which is really important because if Earth were located, say, here, what would be some problems with that?
Be hot.
Be hot, okay, not really. So like this is our galaxy, right? So our sun and everything is right here. It's a small part of our bigger galaxy.
Gravity would get thrown off.
Maybe, I don't really know. I guess
Just
I guess I
numbers.
shouldn't
Basically-
fool the audience on this one, right? But okay, so if we're in a lot more stars,
It's a lot more stuff.
it's a lot more stuff. What's the problem with that? Everything's moving in space,
You
right?
get hit more than
You get hit more,
Yeah,
right?
come on.
So if we were located in
Yeah.
this part
Nailed
of
it.
the Milky Way, there might be more collisions from like comets and other things, right? So it'd be a lot more difficult for the planet to survive because there's a lot more debris and stardust and everything going on in the arms, whereas we're located in between the arms. Okay. The other thing that's really cool about this is that because we're located inside the arm, we can see more of the universe than we could if we were located here, because there aren't as many stars blocking our vision. So we have this better vision out into space, so we can observe more of what God created, which is really cool, right? Okay. The other thing that's really cool about Earth is that it's located very specifically with respect to the
Son.
Sun.
sun.
I knew exactly what you were drawing there.
Thanks, buddy. Okay. So let's go. We're going to go out from the sun. What's the first planet?
Mercury.
Mercury. Good. I had to look that one up. I didn't really know. Mercury. Okay? And then the second planet,
Venus.
Ooh, that's where girls are from.
Venus. And then the third planet.
Mars.
Earth.
Oh, wait.
Hey, hold that thought.
We're rocking this thing.
Okay, so we have Earth. I'll spell that one out. And then,
Mars.
Jacob?
Yes.
Mars. What do we know about the sun?
Hot.
Big and hot.
It's hot, right? So based on the distance we are from the sun, temperature changes, right? So if we are on Mercury, too hot for us,
Too
right?
hot.
There's no way that we're going to be able to exist on Mercury.
Texas in the sun.
And so there's this thing called the habitable zone with respect to each star. So that's a temperature zone where humans could possibly exist, right? Well, thankfully for us, we're located in that habitable zone. Pretty cool, right?
What luck?
So the other interesting thing though is that I saw a couple of different variations of the habitable zone that kind of had Mars included. So as you go further away, obviously it's going to get colder and colder, right? But there is this idea that possibly we could set up a colony on Mars, right? And I think there's even like a legitimate program, like they're going to select
They're,
100 people who are going to go to Mars.
Yeah, like one-way trip.
They ain't coming back.
yeah.
Their goal is to go to Mars and populate it, right, and colonize it.
Okay.
So I don't know how that's going to work, but this is kind of on the border of that habitable zone. So perhaps humans might be able to exist on that. But the great part is Earth is right in the middle. So it's really cool that we have the right temperature, right? Okay. The next one is our axial tilt. Brandon, you're going to make fun of me so bad for this one.
I don't do that.
Out loud.
I'm not doing that.
Okay. So,
Good question on location.
yeah.
So, say the sun is a star. Could it possibly, and so do all stars have this habitable zone around them?
Correct. So all stars have these things that like circulate around them, right? So they all have these planets because stars have this gravitational pull. And so once these things start spinning outside the stars, that keeps them in orbit around the star, right? So all stars are going to have something circulating around them, and they perceivably would each have a habitable zone. But the problem with that is, how do we get there, right? Because our galaxy is so far away from other galaxies that each one has their own star, right? So I don't know distance or how long it would take to get there or whatever, but there would be a position for us, as humans, away from each star, like a distance that would make it habitable based on temperature. But there are so many other considerations that it's just like, you know, temperature is only one thing,
Yeah.
right? Okay,
Back to this axial tilt.
back to this axial tilt business. Whoa. So Earth has an orbit, right? What do we know about Earth's orbit?
Takes a year.
Hey, that's good stuff. Okay?
It's an ellipses.
And it's an ellipses, right? It's elliptical orbit. So it's not completely circular. And it's not uniform around the sun. Okay? So I'm going to need this for the numbers. So on one side here, this is called perihelion. Okay? And that is 147.3 million kilometers, which is about 90
Million.
And I had this in miles on one of them. I guess I didn't say that.
Millen.
Million.
Oh. You think you could do any better?
I liked it.
I think Andrew laughed first.
A million.
That was like the gangster way of saying million.
Shoot, that million. That's a million.
guys doing?
I'm not involved in this ruckus. I'm calling shenanigans.
And this is called a fusion, and it is 152.5.
Million.
I'll talk to you after class.
It's like I'm in grade school again.
Okay. Sorry, this is a very intricate drawing, and I have the added pressure of bringing.
Hey, keep going, man. This is good.
I hope a temple comes up.
That's whenever we'll have some criticism.
I looked up how to do this a little bit.
That's good.
Not really.
Fancy.
Yes. Although the Earth looks a tiny bit bigger than the sun. Just saying there. Just saying.
But it's a million miles closer.
I think the mirrors say the objects in the mirror
Yeah, I
are
understand.
closer than the tree or something like that.
It's good though.
Okay. So the Earth has a tilt. Anybody know what that tilt is?
Acute.
Yeah. I can't remember it. I've heard it before.
Somebody guess.
17 degrees.
No.
I'm gonna say 32.7
Okay. Any other takers?
because I know it's
28.
Okay.
No,
It's actually closer to
42.
60. I'd say.
60.
Come on, I gotta have 3 more guesses. This otherwise it's not fun.
Say
$1.
Yeah.
35.
35.
Ooh.
15.
15. Okay. I don't know who's closer, but it's 23.5 degrees.
I think I nailed it. I think 25 got it.
Okay. The axial tilt is what gives us seasons, right? So as the Earth rotates around the sun, at one point, one side of the Earth is going to be closer to the sun than the other side, right? So if our tilt was 0, all the seasons would be the same, right? So because they would be consistent.
Be like Hawaii.
Well, the middle would probably be like Hawaii, but then the outer parts would probably be
Cold.
really cold, right? Because there's no variation with how close you're getting to the sun.
Mhm.
But because it's tilted, that means over here, the southern hemisphere is closer to the sun, right? Because it's tilted this way. It's not a great drawing. Okay, give me a break.
Hey, hey, nothing wrong with that.
Okay, and over here,
It's all right.
the northern is going to be closer to the sun. This is very important because if it was opposite, then our seasons would be a lot different. Because there's more land mass in the northern hemisphere than there is in the southern hemisphere. And land actually soaks up heat more than water does. Water has a very high specific heat. It's a chemistry term. Andrew, you remember what specific heat is?
Sort of, yeah.
I think
You can say
it's
no.
the amount of energy required to raise 1 gram of water 1 degree centigrade.
Isn't that a calorie? Never mind.
Maybe. Okay. No, that's specific heat. That's a number. Okay? So, but the point
It was
is
something.
that if the northern hemisphere is facing the sun, right, so it rotates more towards the sun, then it's going to pick up more heat than if the southern hemisphere was facing the sun. Which is why it's very important that the northern hemisphere is facing the sun when the Earth is further away from the sun,
Oh, yeah.
right?
Mhm.
Because then there's less heat that makes it to Earth, and so it doesn't absorb as much heat, right? And then when we go around to the other side, it's closer to the sun, so there's more energy hitting the Earth, but the ocean soaks it up and dissipates it a lot more evenly. It's a lot better. So overall, the Earth doesn't go through a crazy temperature change as it goes around the sun, right? So it's based on the tilt that gives it that ability to not be super crazy seasons as it gets to aphelion and perihelion, right? Yeah.
It's maybe way off track, or you may be getting to this later, but I want to ask if you, what about this, like the whole idea of, is it Pangea, is that what it's called, where in the beginning, all the land was together and it slowly drifted away?
Yeah.
Okay, first of all, what do you think about that? And second of all, would that have wouldn't that have changed this whole land mass being in the right place?
Right, but it depends on where the land, like, and I should probably know that.
I'm just curious.
I'm not really sure.
Okay.
Because it probably did happen, right? And then when Noah's flood happened,
Yeah.
it broke everything
Yeah.
apart, and continents could kind of shift, right?
Mhm.
So I'm pretty sure that's what happened. But the thing with that is if that supercontinent is located in the northern hemisphere,
Then it makes it perfect.
it does the same
Yeah.
thing, right?
Mhm.
So then it would be fortunate, right, that it was located in the northern hemisphere so people could exist before Noah's flood. And then when Noah's flood happens, it's good that most of the land is still in the northern hemisphere, right? Which would make sense if that's where it originated anyway. I think that's right, but I'm not
I think that's
100% sure.
Good, just testing your knowledge.
Of course. So those are just three things that are like really cool about the planet Earth, and there's a lot more stuff you can read about as far as like different mathematical constants and how gravity, if that changed, then it would change. You can read about that later. You can go do that. I really believe in it. Okay, so those are just three things, and you can kind of see that maybe there was some creative order in all this, right? But the interesting thing is that if you're a secular scientist, a secular astrophysicist, right, you don't believe in this, right? Yeah, it's great that happened so that we can live here on Earth, right? But if we evolved over millions of years, it happened on this planet. And the argument with that is, well, there are so many planets in the solar system that one of them was bound to have all of these different constants, right? All of these different characteristics. So you can argue all you want about how great it is that the Earth is situated in this one spot, but they're not going to listen to you because they have this probability on their side, kind of. Because the odds against evolution, we'll get into that later, are so far against it, right? But people still believe in it. So that kind of leads us into this transition into the age of the Earth, right? And so one thing I want to reiterate from our first lesson is that the biggest problem with people not believing in the Bible and not believing in starting from the Bible in interpreting all this stuff is that the main problem is unbelief, right? It's not ignorance. People who believe in this stuff are very intelligent. People who believe in billions of years and millions of years are very intelligent. They've gone to school, get PhDs and all this stuff, right? And if you think about it, we talked about the Big Bang Theory. If you leave God out of the equation, if you don't start from the Bible, that's kind of the logical conclusion that you have, right? You have to come up with this naturalistic start to everything, right? So that's what they're working on. They're starting from the assumption that there is no God, there is no divine creator. And so, yeah, that makes sense if you start from that position, right? But we start from the Bible, we start from a God. And so the problem is unbelief. It's not a lack of facts or a lack of ability to convince someone, right? It's the Holy Spirit working on someone's heart, whether or not they're going to believe. Okay? How's it going?
Great, man. Just want to make sure I didn't walk in front of the camera when I
No,
your
it's
tripod
up here.
is in the back of the room. So, just want to make sure I didn't interrupt that.
All right. I'm going to tell you a little story about the age of the Earth. Okay? So this is a secular version of how the Earth came to be, right? I kind of already hinted at it when I went through the Big Bang Theory. Right? What did I say about planets in Big Bang Theory? You remember?
Stardust.
Stardust, right? So that's the cool thing is that, we're all created from stardust, and it's so cool that you're stardust. You can reach for the stars. You like that? Okay. So 4.5 to 4.6 billion years ago.
Billion.
An exploding star in a distant part of the universe, not super distant, pretty close, sent this stardust, right, this collateral from the exploding star in our direction. And it ran into a cloud of gas. Okay? And so this exploding star had a lot of energy coming from it. And it hit this gas, and this gas and this dust from the star started to clump together, okay? And so once it clumped together, now you have some mass, right? And we know that gravity is mass, right? You have to have mass in order to have a gravitational pull. So as this stuff starts clumping more and more together, a star is born, a new star, and that starts having mass and having different gravitational pull on the rest of the stuff that's floating around it, okay? And as it becomes more massive, then it can start doing nuclear fusion, the way that stars generate energy, right? It's by fusing these different atoms together into heavier atoms, but then it gets energy from that, okay? So the star began to perform nuclear fusion, and it still had dust circling around it. So what happens with dust circling around the star?
It's gas.
It starts clumping together, right? And so as this dust starts clumping more and more together, you end up with things called planetismals. You mean to spell that for you?
It won't help.
Okay, so, but it had to wait until everything around it started to cool down, because this has a lot of energy coming from this other star. So as things start cooling down, everything clumps together into these planetismals, and then those can clump together into planets. And then we have different planets in our solar system. Another thing that happened around this time is that the moon came into being. So if you have all these planetismals floating around, one of them apparently crashed into the Earth and dislodged a piece of the Earth. So the moon is actually a part of the Earth, according to secular Earth-forming stories. Okay? And the other thing about this crash is that it gave the Earth its 23.5 degree tilt, because as it crashed into Earth, it messed up its axis, and that's why we have the tilt. Now, the logic behind believing that the moon is part of, or was originally part of the Earth, is that the moon has some very similar characteristics with the rocks that they brought back, and so based on different tests and analysis of that, that's why they think that the moon is part of the Earth. Okay, so I said that the Earth is 4.5, 4.6 billion years old, right? But the big question is, how do they know that, right? Why do they know that? And if you read a lot of stuff about dates of stuff, it's really interesting because the writers just kind of take the scientist's word for it. They write this stuff as fact, and they say, oh, since we know that the Earth is this old, blah, 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 and all this stuff. And it's just interesting that they don't really stop to question it, they don't really stop to think it. Because scientists say it, it's accepted as fact. So, and we'll talk a little bit more about that as we get into some of these other dating things. So, there are two types of dating that geologists use. We're going to talk about the Earth, right? So that deals with geology. So the first type is relative dating. Okay? Now, relative dating has to do with arranging things in order, right? So we're not going to pin a number onto something, but we're going to say this thing is older than this thing, okay? So the first way they do that is by the law of superposition. So if you have a geological formation, right, and you have these different rock layers, the law says that the rock layer on the bottom has to be older than the rock layer on the top, right? Brilliant stuff. I can't, did I write down who it was? I didn't write down who it was. Just brilliant, brilliant scientists, right? They came up with this idea that the deeper stuff was laid down first and then the stuff on top came down second. Just absolutely incredible.
That's amazing.
Okay, so not really super crazy idea, but you know, you got to write it down, you got to make it a law so that other people can use it. But this will be very important as we get into some of these other dating methods. So the second one is called faunal succession. Faunal. Okay? and this is the idea that fossils happen in a distinct order, okay? And this was from William Smith in 1796. And this is based off this idea of evolution, right? So that fossils that are located here at the bottom have died off, right? As these different species have evolved, these different organisms have evolved, the ones that died off were outcompeted by the ones that are above them. And then those evolved into something else that outcompeted them. And then the ones on the top evolved and outcompeted the ones below them. Okay? And so this is, because of this kind of uniformity of these different fossils and how they're laid out in the rock layers, scientists now actually date rocks. Here, we'll put a fossil in there. Oh, that's a terrible fossil. I freaked out there a little bit.
All of YouTube is watching this,
I know.
basically.
Sorry, YouTube. Okay? So scientists now date rock layers based on the fossils they find in them, right? So because there's supposedly this uniformity to how these fossils are oriented in the rock layers. But also, people date rock layers by the, is that what I said?
You got it.
The other way. I don't remember the first one I said.
You got it.
Okay, yeah. People date the rock layers by the fossils. Okay? I don't know if I said the same thing twice.
And the fossils.
Did.
Right.
Right, so it's both, okay. And-
You nailed it.
anyway, so I'm going to read to you this thing that I found. It's not like a reputable website or anything, but it's still on the internet and it claims to talk about how you date things, right?
Wikipedia?
It's not Wikipedia, it's called factmonster.com.
Yes.
That sounds better.
So, shout out Fact Monster.
Yeah.
You're going to get one more hit. Okay, so in one paragraph it says, scientists find out the age of dinosaur fossils by dating not only the rocks in which it lies, but those below and above it. And then, 2 paragraphs later it says, index fossils are fossils that can be used to date the rock in which they are found. So, I mean, you guys are smart. You see the problem here, right? We're using one thing to date another thing, but we're using that thing to date the other thing, right? So when it comes down to it, you have to have a way to date something in order to even set this up, right? And we'll get into that in a minute. But the interesting thing about this is that there's this idea that dinosaurs died off at a specific time in the past. Has anyone ever heard that? What's the date? Does anyone know the dinosaur date?
Sure don't know that.
We don't know this.
We learned about dinosaurs.
Yeah, we didn't learn about that in biology.
No, we didn't.
Okay, so but there's the prevailing thought about the extinction of dinosaurs is that it happened 65 million years ago when an asteroid hit the Earth and caused this great dust cloud to go up into the atmosphere, okay? And so as the dust rose into the atmosphere, it covered the Earth. And if you cover the Earth, what's going to happen to the Earth's temperature? It's going to drop, right? Because that dust in the atmosphere is going to block the sun from getting to the Earth. And then that's like this winter that's caused by the meteorite hitting, and then everything starts dying. But then there's also this idea that even after the dust cleared, that some of the greenhouse gases disappeared or something, and then there was actually an increase in heat after the winter. So the things that didn't die during the winter actually ended up dying during the intense heat afterwards. Okay? And so there is, and this happens supposedly in, I guess I should write it down. And then we'll get somebody to pronounce it. Any volunteers?
We don't know what it is
Jacob.
yet.
Jacob will say it.
So is this
Nope.
like, this is the accepted theory by mainstream science?
This is the accepted theory by mainstream science. And if you read articles, if you type in, any takers?
Chicula, Mexico.
That's not bad.
Did you see the X in there?
It runs together.
So yeah, if you go type in to Google what happened to the dinosaurs, right? You're gonna come up with a bunch of articles
Chicxulub.
that talk about this
That's it.
meteor hitting Chicxulub,
There's no X, it's a sound.
whatever, hit this place in Mexico, right?
I would know.
You would know, it's true.
Chupacabra, Mexico.
I'm kind of in the middle of something else.
Hey, don't
Okay,
embarrass me
so
in front of you.
if you read about this, this is what it says. This article is going to start off by saying 65 million years ago, this meteor came and hit Earth at this place in Mexico, and it caused the extinction of the dinosaurs. And they will talk about that as fact, even though, you know, how can they possibly know? We'll get into that here in a little bit. I'm getting ahead of myself a little bit. Okay. The other interesting thing, you know, in that quote, it talks about index fossils. So those are the fossils that I was talking about, like as far as the layers go. If you find this fossil based on the layering of those fossils, it means that that rock is X amount of millions of years old, right? Because those fossils, those organisms existed at a certain time and all died off. But the problem is, what if they all didn't die off, right? So there's this fish.
Uh-oh.
Man, these words are just insane. It's called the Coel.
Coelacanth.
Yeah, there you
That's
go.
it. I've heard of that. Yeah. That'll be weird.
Right? So this is a prehistoric fish that apparently they believed had become extinct 66 million years ago, right?
Oh.
In 1938,
Caught one.
they caught one. And in 1997, another one showed up in a fisherman's net. Okay? So
Whoops.
it's really interesting that they can use these index fossils with absolute certainty, which is what they do as far as dating things, when there's no way that you can possibly know that nowhere in the world one of these things is still hanging around, right? And if one of them's hanging around, that means something else probably gave birth to it, right? And so you have this line from even when you thought they existed to the present time. So if you find one in a rock somewhere, it might be from 50 years ago, right? So there's this really kind of weird logic that they use as far as, oh, we're certain that these don't exist anymore. But if you read about it, they talk about this stuff as fact. So it's kind of scary, really.
Would they say that like it re-evolved? Like it was
Yeah,
extinct and then...
and so so they talked about like the fish that they caught, how they're different from the ones in the past. So they've evolved different stuff. So they're not the same thing, but they're part of the same family of fish. And yeah, I mean, they're obviously going to have different ways to explain it away, right? Because that's kind of their job. Okay, so that is relative dating. The second kind is absolute dating. How are we doing? Thanks. All right. So absolute dating is where we're actually going to pick up a rock and give it a number. Okay. The overarching idea behind this is called uniformitarianism. You might want to spell that out, or
I got you.
okay. I'll do it. I could write it off straight off this piece of paper. if you want to. So the idea behind uniformitarianism is that everything that we work on now as far as science, we have to have a basis for seeing it now and then extrapolating backwards. So geologists in the late 18th century or 19th century started looking at different natural processes, and they said, okay, so we see this happening now, so that's how we got from the past to where we are now. So that's a terrible explanation, so I'll just read a quote. This is by James Hutton, and he's one of the original geologists that kind of started this uniformitarianism movement. And he says, the past history of our globe must be explained by what can be seen to be happening now. No powers are to be employed that are not natural to the globe. no action to be admitted except those of which we know the principle. So it's this whole idea that, we talked about at the beginning, that if you leave God out of the equation from the beginning, and you're living here on earth, these questions are ingrained into every human being. Where did we come from? How did all this start, right? So these people are trying to search for that apart from God. So they arrive at these different conclusions based on their observation, because that's all they have, right? They don't have anything else telling them how it all happened, what happened in the past. So they really have no choice other than to arrive at the conclusions that they're making. So, yes. So there are two different forms of it. One is naturalistic uniformitarianism, which basically leaves no room for anything outside of what we observe. But they're just regular uniformitarianism can leave the door open for cataclysms, kind of like the flood. So some people who hold to this belief may say there might have been floods that happened in the past that kind of shaped some of our geological structures. But naturalistic uniformitarianism doesn't believe in anything close to a global flood whatsoever. So if we're going to start assigning numbers to stuff, how would we do that? What's your best idea?
I don't have an idea.
So if Earth started, oh, you had an idea?
Shh, people.
What's your idea?
Like you find something that you like know for sure, like that you've observed, and then see if you can find it anywhere else. Totally makes sense in my head.
Okay, that's good. That makes
Also,
sense.
everything has to have something in common that you can compare it to each other.
Those weren't really answers I was looking for.
How about carbon-14 dating?
Not quite yet. We're good.
Alright.
So, the thing that we talked about this with the universe, that we're looking for the age of the universe. So you find the oldest star, right? You're looking for the oldest star, and then the universe has to be older than that. So the same thing with the Earth. Basically, you pick up rocks and you date them using methods that we'll talk about, and then you try to find the oldest rock. And then once you find the oldest rock, that's kind of the age of the Earth. So the oldest mineral ever found on Earth is 4.2 billion years old, according to dating methods that we're almost to, I promise. They've also dated moon rocks based on these methods to 4.5 billion years old. And so that kind of gets us closer to the actual age of the Earth that they claim of 4.5 to 4.6 billion years old, right? So based on that idea that the moon came from the Earth, so we can date the moon and get an accurate date for the Earth. But how, nope, that's not the next page. Kind of freaked me out there for a minute. So, but how do scientists do this? Chemistry review. Who's ready for some chemistry? Andrew, I know you're ready for some chemistry.
Not me.
I barely passed.
What are the components of an atom?
Protons
Okay, where are protons located?
in the middle.
In the middle. I'll use colors. I'll use colors.
And
Okay,
then
protons.
got your old neutron, old Johnny Neutron hanging out in
Jimmy.
there. Jenny? Who's Jenny?
Jimmy.
Jimmy. Old Jimmy.
Okay, neutrons.
I don't know. Who's this guy's on?
What else?
Electron.
There they are.
Electrons. We're actually going to do two. What do we know about electrons and protons?
Electrons are negatively charged and protons are positive.
Also, they kind of
Nailed it.
Around.
go together, right? They're
I
usually
nailed
the
chemistry.
same number, right? Because protons have positive, electrons have negative, and so they kind of balance each other out, right? Their charge kind of balances each other out. So based on the number of protons that are in the nucleus, which kind of directs how many electrons are in the atom, that's where each element gets its chemical properties, right? So this, do we know this element?
Helium?
Helium, right? So helium is the second element on the periodic table. It goes hydrogen, then it goes way over here to helium, and then we go back over here and start going over. So this is helium because it has two, I'll do this in black so nobody gets confused. So this is helium, and it has an atomic number of 2, which is the total number of protons. So we put that here. But it has,
H-E?
what's that? Yeah.
Just say.
Here, you wanna finish it?
No, go ahead this time. I get it next time.
Okay. But it has an atomic weight of 4 because it has protons and neutrons. So they're pretty close in mass. So we add them together and that gives us an atomic weight of 4. Okay? Any questions? I want you to stay with me.
Electrons don't have hardly any mass.
Right, because they're so far away, and they're kind of orbiting, so they don't really give any mass to the actual element. So, based on the number of protons and neutrons, each element has its own chemical reactivity, and that gives us the ability to make different molecules like DNA, right? And protein and sugar. All of those are made from elements, and they arrange themselves in such a way based on this part of their structure. Okay? But there isn't just one form of each atom, right? There are things called isotopes. And those are varying forms. And so we're actually going to talk about carbon, because that's the one I know best. Okay? Carbon has a atomic number of 7, and the most common isotope has an atomic weight of 14. And that means, what does this 7 mean?
7 protons.
7 protons. And these aren't all oriented like this. I'm just doing this for the ease of the drawing. So we have 7 of each. But a different isotope can vary in the number of neutrons because they don't give the element any charge, right? Protons give it a positive charge, but if you add a neutron, it doesn't change the charge of the atom. So it doesn't change its chemical composition, it doesn't change its chemical reactivity. So it's still carbon, however, instead of, no wait, I did this wrong. It's 6. Ah. You guys. Like I said, carbon has 6 protons and 6 neutrons. Right? But if you add a neutron, then the atomic mass changes to 13. You can also add another neutron, right? It's still carbon because it still has 6 protons, but it has a different mass. So it has a mass of 14. That's what messed me up earlier. So the interesting thing about this is you can measure this minuscule mass change based on the different molecule that it's in. So there are 15 different isotopes of carbon, so 15 different ways of orienting neutrons. A lot of them are synthetic, so you make them in a lab, and then they're not very stable because the stability of an atom is based on the ratio of protons to neutrons. So since the ratio is out of whack because we've added these 2, then that gives it instability. Atoms want to be maintained at the lowest energy state, so this has more energy in the nucleus because they're trying to orient themselves in a lower energy state, but it doesn't work because there's more neutrons and protons. Does that make sense? I'm getting a lot of blank stares because I'm just blitzing through this stuff.
That's just my face.
Okay, so the three isotopes of carbon that really matter for us in nature are carbon 12, which is regular 6 and 6, right? Carbon 13 and carbon 14. So carbon 12 accounts for about 99% of carbon, and then carbon 13, naturally there's about, I think this is, sorry, 98%, and then about 1% and about 1%. And so these aren't very abundant naturally in the earth, okay? So we can use that to our advantage. Also, carbon 14, sorry, I'm trying to, man, I'm getting super ahead of myself here. All right, we're gonna back up a little bit.
It's good.
Which way am I gonna go here? Let's talk about decay first, okay? So I talked about a little bit about decay, and that's how we're gonna use rocks and ages of rock, or we're gonna arrive at ages of rocks, is through radioactive decay. So I already said that radioactivity is based on the stability of the atom and its desire to decay back into a different atom. Okay? So because this has extra neutrons, it doesn't want to stay like this because the ratio is different. So what can happen is the neutron can actually undergo beta decay. Don't ask me how that works or anything like that. But it can actually go and turn into a proton. Crazy stuff, right?
That's banana.
So we just added a proton. What happens to this element now?
It's a different element.
It's a different element. What element is it?
Oh. That's what's different.
Nitrogen.
Well, then that's a nitrogen, isn't it? Look at that.
Okay? So through these decay and through this changing of an unstable element into a stable element, there's an actual change in what element it is. So because of this, that's this idea behind radioactive decay or radioisotope dating. Okay? So there's, I'm going to give you a quick list of some of the different dating methods. So first we have uranium 235 to lead 237 or 207. So there's a big difference between these numbers, right? So as they decay over time, it transitions to different elements and then it stops at lead. This is a stable element. So over time, we can see this decay from uranium to lead. That's observable. And we'll talk about that here in a little bit. But this has a half-life of 700 million years. Okay? What is the half-life? Does anybody know what a half-life is?
Time it takes for half of it to decay.
Half of it to decay, exactly. So it's kind of a weird concept to think through, but every atom that is radioactive is unstable, but it doesn't automatically decay to the next element, right? So it's kind of this chance thing that happens, but there's enough of a chance that over time we can measure how much of that element will turn into this element. So this is called the parent element, it's called the daughter element. And we can measure both of those and arrive at a half-life. Now, you see this half-life of 700 million years, and you're like, well, how do they know that? But you can measure it over a finite period of time and then extrapolate that and end up with a decay rate, right? So if you have, say, and these are just atoms. So if you have 5 atoms of uranium and you measure over time that one of them turns into lead, right? And let's say you measure that over 100 years. Not really because of this one. But then we can say, we can actually come up with a time that it would take for
250
half
years.
of them,
250 years.
250 years to turn into, and I probably should have made this 6, right? So if we measure this as 50 years, we can say it's 150 years for all of them, or for half of them to decay. So that's the half-life. Does that make sense? Another one is uranium-238, which decays to lead-206 in 4.5 billion years. Another one that is used a lot for rocks and stuff is potassium argon dating. Have you ever heard of that? Somebody ever heard of that? So the interesting thing about this is that the weight doesn't change. Very similar to the carbon into nitrogen, right? So this is once again going to be just a transition of a neutron into a proton, rather than in this case, this undergoes alpha decay, which is just ejection of protons and neutrons from the nucleus. And that's why you have this drop in atomic number. And this half-life is 1.3 billion years. And then we've already talked about this one from carbon 14 into nitrogen. And this half-life is 5,730 years. So a little more manageable. How are we doing on time? 6 minutes. Okay, I can do this. So based on the amounts of these different elements in rocks, what they do is they measure each element and then they kind of make a ratio, and then from that ratio they decide how old the rock is. And it's really interesting the way they do this, because there are a lot of assumptions they make, right? So we talked about, I think 2 lessons ago when I did the hourglass, right? I drew the hourglass just for my man Brandon over there. Pretty good hourglass. So what were the problems with the hourglass? And just for anybody who wasn't here, so I'll just draw it.
Hey, you want to draw that?
I'm good. See, create it.
So the idea is you come into a room and you see an hourglass and you see sand falling through it, right? There's some sand here and there's some sand here. And you're asked, when was it turned over, right? Well, you could measure the rate at which the sand falls through, but what if it wasn't full in the top? What if it wasn't empty in the bottom, right? So how can we know exactly, what if the rate was different? What if this changed, like the width of the spout changed, right? So there's differences that we can't account for if we walk in and just see it happening, okay? So it's very similar with these dating methods. So the idea behind them has a lot of assumptions. The first one is that there were only parent atoms present in the initial sample. And so the only real kind of rocks that they like to date are igneous rocks, which are formed from heat, like volcanoes and stuff like that. So the idea behind that is that the heat that formed this rock and then it cooled, but before it cooled, so if we have a rock, before it cools, the different daughter elements that are already present in the rock are able to escape. Okay? So all we're left with now, because they're gases, so this would be like potassium argon dating, because argon is a gas. So if you heat this rock up really hot, the argon is going to go out of the rock because it wants to escape. And then as the rock cools and solidifies, the assumption is that there is no longer any argon in the atom, or in the rock, okay? And then as you, I did that wrong. I got them mixed up. But the point is that the assumption is that the daughter elements escape from the rock, and so you're only starting with parent elements. Okay, what's the problem with this?
You don't know really the
we don't know if they're really all gone, right? We weren't there 4.6 billion years ago, right? So this is based on different observations in the present that if they form a rock this way, then the daughter elements escape. But we don't know that that happened in this rock that we're picking up off the ground, okay? Another assumption is the decay rate. So we can measure the decay rate right now, but what's to say it wasn't different in the past? Okay, so based on different characteristics of like the Earth's magnetic field and different things like that, the decay rate in the past might have been different than the decay rate now. Especially if we're going to talk about billions of years. Let's hypothetically say that that's true, right? How can someone say without a doubt that the decay rate now is the exact same as it was in the past? And so the interesting thing about that is if you use different dating methods, so if you use uranium and potassium argon dating methods on the same rock, oftentimes they don't match, which is insane, right? So you would think that if this rock formed and all the daughter elements escaped, and then we measured the different daughter elements and parent elements, and that we know the half-life, then we should be able to say the rock is this many years old based on all of these different dating methods, right? They should agree because we're making all these assumptions, right? And so, we don't know that the decay rate is the same, and if it wasn't, since they're different, if they were all sped up, then it would change the dating of the different methods. That was really confusing, probably. Also, there could be different environmental factors that come into play. So if water washes over the rocks or something, water cuts through the rock, there might be different contamination from the environment. And so we don't really know whether or not these assumptions that we're making are true, right?
So scientists just like they don't take this into account, or like they just say, oh well, it's not that big of a deal, or like.
Man, I don't really know, but here's this thing that I found on the U.S. Geological Survey website. So this is our government, okay? You guys are gonna
Nothing
love
good
this.
ever starts there.
So it says, if we know the number of radioactive parent atoms present when a rock formed, we have no idea, right? But we're assuming that we know that. And the number present now, we can calculate the age of the rock using the decay constant, which we have no idea. That's the same in the past. The number of parent atoms originally present is simply the number present now plus the number of daughter atoms formed by the decay, both of which are quantities that can be measured. I agree with that part. That's the first part that I've agreed with so far. Samples for dating are selected carefully to avoid those that are altered, contaminated, or disturbed by later heating or chemical events.
How is that?
How on earth are you going to be able to go up to a rock and say, this is the one that was not altered, contaminated, disturbed? There's no way to know that, right? Especially if we're going to talk about billions of years. You would have to know, you would have to have a video of that rock and know that there was nothing that altered it, nothing that touched it, right? But, as I said right from the beginning, if you're going to take God out of this, this is your only option, which is really the sobering truth of this, is that you can't arrive at any other conclusion than what scientists today are arriving at. Because they're smart, right? So all these smart people are agreeing that this is what happened because this is the only logical conclusion based on the evidence that we have on the earth, right? We all have the same evidence. It's just a matter of how you interpret it. It's where you start. Do we start from the Bible? Do we start from, the age of the earth according to the Bible, which we'll get into next time? Or do we start from this naturalistic uniformitarianism where we observe natural processes, we see them now, they must have been going on in the past, and that's how we got to where we are today. Okay, so I hope that was somewhat clear. Next week, not next week, in 2 weeks, we'll talk about carbon-14 dating specifically, and we'll get into a little more clearly how that works, and we'll blow your mind with some carbon-14 dating. And then we will talk about some creation theories, and kind of look at that, and then we'll get into evolution. Just for you.
Excited. I'm
Okay?
ready to evolve.